Did you know that US general hospitals save about 137 terabytes of data every day? That's about 50 petabytes of data every year. And imagine if we multiply that with 6,000 hospitals across US. That's huge. Looking at the scale, we have a huge gold mine of data, but are we able to use that? The current healthcare systems are set up to work in silos. So what if we can create a standard, some governance principles to unify all of them, create some use of PET to have them work together? We can create a clinical AI that can be used by all clinicians to improve efficiency. That's efficiency and that's impact. I think the requirement is there, and also the data is there. So what should we do? What can we do? That's what we'll discuss today. So the agenda. So what, why, how of this problem? And the core of it is the data and interoperability. And the next part is the technical and security overview. We'll also talk about the privacy aspects in it, and we will cover the real world challenges in future direction. So as I said, in US, there are regional centers called HIEs, Health Information Exchanges. They get data from community hospitals and regular hospitals, but they work in silos. So why is that happening? I mean, as you might know, there are a lot of regulations in healthcare, so we can't aggregate data to a single location. So how do we work with it? So let's set something straight here. The thing that I want to set straight is, first, healthcare data is complex, temporal, and hierarchical. With that said, in order to get collaborative AI to work, it resides on 3 pillars: standards and interoperability, and governance, and the choice of PET, whatever we select. But let's talk about standards and interoperability. When we talk about this, the first thing that we get to mind is ASTP's 21st Century Cures Act. At heart of it, they want to promote openness in sharing, so that they created something called FHIR APIs, FHIR. It's a standard to transfer or interact clinical data. So with standards and interoperability set, so next topic is data governance. For data governance, we use something called VSAC value sets. Value sets are defined by clinicians and doctors, so whatever is defined there represent the real world implications. So why are we saying all this? This is the core pillar to help the hospitals to work together in a privacy setting. So what we used is like open source VSAC value sets, and we also created few value sets for our study. And at the end, as I said, privacy creates trust when hospitals work with each other. So we selected split learning for it. We can use any PET technology here. And this is the project process flow. I'll go very quickly on this. The green box that you see is the entire DMZ of any hospital or engaged organization. Here it is HIE, Health Information Exchange. The blue that you see is similar to a data clean room. It's a central server, just like in federated learning. When it comes to green box, there are numbers from 1 to 6. They are the data transformation pipelines. Some of them relates to privacy. Basically, I'll go very quickly on 1, 2, 3, 4. They're basically pipelines, data pipelines to make sure we remove anything that's unnecessary for the study. So we are starting with privacy, and structure them with something called CQL, clinical quality language that enables the layered approach of governance. The sixth process, from 5 and 6, it's staging, and sixth is where the notes field, the de-identification of notes field happen. So we used a combination of DI transformer model, and we also used regular expressions to scrub any identifiable information from it. And we also obfuscated the data before converting into 768 dimension using clinical BERT model. So we'll talk about split learning in a later phase. So 7 and 8 is basically split learning happening across for AI training or machine learning training. What data we used? We used multimodal, continuous variables, categorical variables, nodes. So for continuous and categorical conditions, basic healthcare information like labs, symptoms, and additional lab elements like arterial blood gas and etc. For notes, we de-identified, as I said, de-identified and obfuscated the data and converted to 768 dimensions before feeding into the notes vertical of the process. It's all normalized and standardized before feeding into the neural networks. So let's talk about split learning quickly. Why split learning? What is it? So split learning is a distributed deep learning. So it gives more control in how we process our models. So in a split learning, you have all the layers set up as L1 to SM. So your input and labels reside in an entity. So in our case, there are 3 HIEs. So all of the information, private information, stays within the boundaries of HIEs. There is no aggregation. Only the activation and gradients move back and forth. That gives a bit of customization for the engineers. And next, the why split learning. So what we found is split learning is much faster when compared to other comparable technologies. So in our process, we were transferring about 2 kilobytes per minute batch across internet because we had organizations across boundaries. Contrast to that to something like a federated learning, it will be gigabytes of information, the whole model moving across internet. Again, one other point I want to focus here is in this process, we have to split the computation graph because we are splitting in different organizations. So it's our duty to maintain the computation graphs. There are 2 splits as you see. There will be input computation graph, there will be labels computation graph, and there will be a central server computation graph. And then we can maintain them. Let's quickly talk about the privacy engineering decisions. In this context, we use semi-honest situation. We had an MSA. On top of it, we layered data and also model considerations. Let's talk about data. In data, we first started with high trust compliance, which requires safe harbor, which means removing all 18 elements, identifiable elements from the data. We started with that. And then we also observed that notes had PHI. So we used, as I said, regular expressions and DI model to scrub the notes and then obfuscated the data. When it comes to model, the primary principle here is the HIEs, each one cannot communicate with one another. That's the primary premise of the MSA that we had. So there's no absolute communication between them. That required us to work in a client-server setting with clear demarcations. At any time, HIE1 or HIE2 or HIE3 could only connect with a central server for learning. Our security stack used high trust compliance FedRAMP certified systems. So basically TLS 1.3 plus, and also GitHub security, compliant with high trust. For, we used Codeci for code verifications and vulnerabilities. Again, Kubernetes cluster, everything is FedRAMP certified. We also use something called node isolation with OTP process. So the central server knows exactly who is connecting, what is connecting, and there's only registration process before connecting to the central server. That removes man-in-middle attacks and also some part of FSHA, feature space hijacking attacks. And to the empirical side, we implemented the no-peak split learning from Praneeth, MIT student. So we use the structure there, and it's basically using distance-based decorrelation of intermittent features to enhance the privacy. This is a quick architecture diagram. I'll post it. So basically, the one thing we can look at here is as I said, each of the computation graph will be broken. So it was the tough part where we should maintain the computation graph separately and then link up to the model to get the model learning. So for HIE collaboration challenges, as we set the context, the healthcare industry, it's hard to get any collaboration. So there were strict data clauses, which required us to work with general counsels and create a custom MSA. The MSA had clear demarcations of who does what on which side, like HIE side and also central server side. That gave us, our opportunity to work with the HIE partners with SOWs. This also meant that we had zero visibility into data. The researchers didn't have visibility into HIE's data. That rendered regular data analysis and other techniques irrelevant. So we had to rely heavy on our healthcare knowledge and also standardization that I talked before, the value sets. But before we learn, the one thing that we should be careful about is how we maintain the data quality. If we cannot see data, how did we maintain data quality? For that, we relied on summary reports from FHIR and VSAC value sets. So we were looking, there was no PHI, it was all aggregated level. Our experience from both sides, technicians, clinicians, we saw the aggregated information, saw where the gaps are, and we found some code coverages and terminology alignments, discrepancies. So we set out to solve them. How we solve them, we standardized line codes for lab data, and we corrected. We resolved a lot of measurement discrepancies as well. We found problems when the data is flowing from FHIR bundles. And lastly, the QA check. So we aggregated all of the information in regions and then verified against the CDC reports. So any disparities between what we are seeing in the real HIE side and what we are seeing in CDC side, we found any discrepancies, we corrected them. Finally, when it comes to technical implementation hurdles that we had, we started with PyTorch RPC implementation because it allows us to do data parallel, model parallel architectures. It was based on P2P, peer-to-peer networks, but we had a strict clause where server and client relation is required. So we had to pivot towards WebSocket using WebSockets. And also the second aspect of it is the split learning process was not using all GPUs when processing. So we had to create a sharding process, a custom sharding process based on how many GPUs are available at each location. The core of it is that we had a shard spawner and also a registration task queuing mechanism at central server, which knows at all times where each HIE is connecting from. There is also the same OTP process that connects each of these shards to the central server. So every process is done in async. So this is work in progress still, but this is at the core of our implementation to maximize the learning process in split learning. Quickly touching on results. So we started out with disease diagnosis. So we had 5 comorbidities that we started out. One of them is myocardial infarction. And as I said, there is categorical data, continuous data, and clinical text data. The learning process we could successfully train, and the next future steps is to develop the multi-GPU optimization, and we want to do a red teaming effort on making sure that the data we train at split layers are not leaking any data, and also include differential privacy inspired activation functions just before the split layer. Finally, I wanted to say that we want to work on the split learning so that a lot of other healthcare organizations can work together on this broader impact for broader impact. Thank you.